This lesson is the beginning of Unit 2, and in this unit, we're going to be learning about energy and scientific measurement. Energy and scientific measurement. Energy changes in matter is what we're going to focus on this slide. And if you recall from the last unit, we learned about chemistry, what chemistry is, the branches of chemistry, and we talked a lot about how chemistry is the study of matter and the changes in matter. We talked about chemical changes and we talked about physical changes. In this lesson, we're going to focus on energy changes in matter. Energy is the ability to do work or to produce heat. The ability to do work or to produce heat. So you have the ability to do work. You're actually doing work right now while you're taking notes. And we're going to define work in just a second. And you will see what I mean by that. But we as people, we do work. Your computer is doing work. It's also producing heat. Therefore, energy is being used or utilized in those processes. So we're going to focus on what exactly is work. Work is the capacity to move an object over a distance against a resisting force. So as you are writing your notes on your paper, you are moving your pen or pencil over across your paper over a distance against a resisting force of friction. So you're doing work, your schoolwork. If you were to push a lawnmower, obviously you would feel that you're doing work because you would get tired if you did a lot of push mowing. But work is the capacity, the ability to move an object over a distance against a resisting force. You don't actually have to be moving it though for it to be classified as energy. And we're going to explain what I mean by that in just a second when we look at the three basic forms of energy. The first is called radiant energy. And radiant energy is energy from the sunlight or from a light source. You often hear of the sun radiating heat, or you hear of a radiant heater. Sunlight is classified as radiant energy. And then we have kinetic energy. Kinetic energy is the energy of an object that's in motion. So, for example, a car riding down the road or a ball being thrown across a baseball field or a basketball being thrown as you shoot free throws or a golf ball rolling on the green. Your pencil moving over your paper. The energy of an object in motion is exhibiting kinetic energy. Now, there are very specific types of kinetic energy, and I've not listed all of them here, but you can have mechanical kinetic energy, like when your engine is running in your car, or when a fan is running, the fan blade turning. That's mechanical energy. Thermal energy, like energy from a flame, or from a toaster oven, or from a heater, thermal energy. There's chemical potential kinetic energy. There's many types of kinetic energy, but if the energy is having to do with anything being in motion, then it's kinetic energy. And then we have potential energy. Potential energy is stored energy or the energy of position. There are also some specific types of potential energy, like gravitational potential energy. Like if you think about an apple hanging in a tree, Gravity is a force acting on it, but while it's just hanging in the tree in a fixed position, it's exhibiting potential energy. If it were to fall to the ground, it would then be moving and it would then be classified as kinetic energy, and that would be gravitational kinetic energy. If gravity is acting on the object, it could be gravitational potential or gravitational kinetic energy. Electrical energy can be potential. If you have a light switch turned off, then that's electrical energy being stored. But as soon as you turn the switch on, the electricity will begin to flow and it will then be kinetic. You also can have chemical, like in your batteries in your calculator. If your calculator is turned off and the battery is not being utilized at the moment, then that chemical in the battery has potential to do work, but at the moment it's not until you turn it on. Then it's converted to kinetic chemical energy. So the kinetic and potential energy, they can be converted from one form to another. So I want you to pause this video for just a little bit and take a moment to write these examples down in your notes. And then once you write these examples down, I want you to try to classify them as to whether they're potential energy. And if you think it's potential energy, you can put PE. Kinetic energy, if you think it's kinetic energy, you can put KE. Or radiant energy, if you think it's radiant energy, you can put RE. So write these examples down and then classify them. Pause the video while you do that. And then once you've answered these questions, resume the video and then check your understanding of these concepts. I'm going to go ahead and go over the answers. So assuming that you are coming back after pausing the video, a book resting on the table, if it's at rest, that's got to be potential energy. Hopefully you said PE for that. Water stored behind the dam. The verbs kind of give it away. If the water is stored, it's not falling, so its energy is not being harnessed at the moment, but it's got the potential to be harnessed, so it's potential energy. Water released from the dam and falling, there's your motion, to a lower level, that would be kinetic energy. And that would be gravitational kinetic energy because gravity would be acting on it. Energy stored in a battery, that's going to be potential energy. Energy in gasoline or in the food that you may eat but you haven't eaten it yet, that's potential again. A moving locomotive is in motion, so that's kinetic energy. Sunlight striking a solar collector. Maybe you have a solar panel on your calculator, or maybe you have solar panels at your house. When the sunlight strikes that solar collector, it's collecting the radiant energy. Hopefully you call that radiant energy because it's coming from the sun. And then an apple falling from a tree, if it's falling, then it's going to be kinetic, and specifically it's that gravitational kinetic energy that we talked about. All right, so hopefully you understand the way to categorize kinetic, potential, or radiant energy. Now, how do we measure energy? Chemistry is a quantitative science. So in this unit, we are focusing on measurement and quantities. And so the first measurement we're going to look at here is how we measure energy. One common unit of energy is called the calorie, and it's abbreviated CAL. Now, if you look on any nutrition label for food, you're very familiar with calories. Whenever you read your nutrition label, maybe you're watching your calorie intake, your caloric intake. But think about it. The food that we eat is what helps provide us with energy to go about our daily lives and do the tasks that we need to do of a day. So calorie is a unit of energy. I don't know if you've ever thought about it, but if you have, or maybe you haven't, but calories have a definition. If you have like 500 calories in a candy bar. That's a lot of calories to intake at one time. But the way those are determined is with a device called a calorimeter. And the scientific definition of 1 calorie is it is the amount of heat that will be needed to raise the temperature of 1 gram of water by 1 degree Celsius. The amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. That's a calorie. So that's a common unit of energy. But in science, we like to use the SI units of energy and the SI units of measure. So in your vocabulary that you defined over the last night's homework, this was one of the units or one of the terms you defined, the joule, Joule. Now the symbol for the joule is a capital J. Joule is the SI unit of energy. So SI is your International System of Units. So we're going to learn about SI units as we go throughout this chapter, and we'll add to some of our SI units in later chapters as well. But you want to make sure you remember the SI units. For energy, it's the joule. Now, since we have 2 units of energy that we talk about in this class, we need to be able to convert between these 2 units. So we need a conversion factor to do that. And this is one you're going to want to memorize by the end of this chapter because we're going to be using this to do some conversions a little bit later on. So 1 calorie, so the food calories I was talking about earlier, 1 calorie is equal to 4.184 joules. If you have 1 calorie, that is equivalent to 4.184 joules of energy. Now this leads us to another law. So in the last chapter, we talked about the law of conservation of matter or law of conservation of mass. Here, we're looking at the law of conservation of energy. So the law of conservation of energy says in any process, whether it's a chemical or a physical change, energy can neither be created nor destroyed. In any process, energy can neither be created nor destroyed, but it can be transferred or transformed from one form to another. So it can be converted from one form to another, but you always can account for the energy transformations. So for example, if you consider lighting a match, if you have a match, then you have potential energy. In the wood, that's the chemical potential energy, and on the tip of the match, you have the red tip. That's actually the element phosphorus. So that's also chemical potential energy. Now, when you light the match, you're moving the match over a distance to strike it against the resisting force, and it's going to ignite. That potential energy, when it ignites, changes to kinetic energy. So in the matchstick, you have potential chemical energy, and that's in the wood and in the phosphorus on the tip. So the red tip on a match is phosphorus. You have chemical potential energy. And when you strike it and light the match, it is converted to heat and light energy, and that's classified as thermal energy. And if you think about a flame flickering, that would be kinetic. It's a specific type of kinetic energy. It's called thermal energy. So we can account for the energy transformations that take place. All right. So then what about if we want to trace the energy changes within a flashlight? Trace the energy changes within a flashlight. Well, if you think about the flashlight, try to kind of draw it here a little bit. If this was a flashlight, and again, don't judge my drawing skills, y'all. If this is a little flashlight, and of course you have your batteries in here. I'll put battery, battery. And then of course you have your light bulb with your little filament here. So let's say you turn the flashlight on and the light turns on. Okay, so let's trace the energy changes that occur in the flashlight. First off, in the batteries, you have chemical potential energy in the batteries. When you turn it on, it changes to electrical because the electricity starts to flow, and it's kinetic. And then, hopefully you also said radiant because there's light, and that's kinetic. It's moving, radiant, it's radiating, thermal energy. So you can account for the energy transformations that occur. Now, I also said that there are energy changes that accompany chemical and physical changes. Energy changes that accompany chemical and physical changes. One of those terms is called endothermic, and an endothermic process is any process that absorbs heat. Now, the prefix here is endo, and then you see the root word thermic. Now, this is where we get thermal. Think of the thermometer. That means heat. Thermic means heat. And endo means it brings it into the system. So if you think about if this were a little reaction chamber, and if energy was being absorbed into it, it's called endothermic, if it absorbs energy. Any process that absorbs energy is called endothermic. And then we have exothermic processes. Here you see the prefix exo, which means it exits. So in an exothermic process, energy is released. So if it's exothermic, the energy would be released out of, it would exit the system. And so it would feel warm to the touch. If the energy is exiting the system and you were to put your hand on it, then it would feel warm to your hand because the energy would be exiting the system and it would be going into your hand. If you were to touch an endothermic process, a container in which an endothermic process was occurring, then that would feel cool to the touch because it would literally pull the heat out of your hand into the system. And if it pulls the heat away from your hand, it's going to feel cool to the touch. Now, in the last chapter, we talked about phase changes. We talked about solid changing to liquid, liquid changing to gas, gas changing to plasma. And then we also talked about if you were to reverse that and go backwards, plasma to gas, gas to liquid, liquid to solid. So there oftentimes you're going to need to be able to tell me if a process was endothermic or exothermic. So with your phase changes, this is a little shortcut, if you will, or a little visual to help you remember, because sometimes this is something that it's easy for students to get confused about. So if I were to ask you solid changing to a liquid, we call that melting. If I were to ask you melting, if that were endothermic or exothermic, think about that for a second. Melting. So for ice to melt, what? does it do with the energy? Well, in order for it to melt, it's going to have to absorb energy. So absorbing energy is always endothermic. So if you're going in this direction, it's going to be endothermic. Same thing is true going liquid to gas, endothermic. Gas to plasma is also endothermic. So anytime you're going in the forward direction, that process is going to be endothermic. It's going to have to absorb energy to get to the more energized plasma state. Now, if you're coming backwards, if the plasma is going to change back to a gas, it's got to lose energy, exothermic. If the gas is going to change back to a liquid, it's got to lose more energy, exothermic. If the liquid is going to change to a solid, it's got to get cold, y'all, exothermic. So this little visual, if you will, if you put the states of matter in order, solid to liquid to gas to plasma, anytime you're going in the forward direction is always endothermic. Anytime you're coming in the reverse direction is always exothermic. The last thing we're going to look at in this lesson is heat flow. Now, at the top of this slide, you see a camper, and he has apparently it's kind of cool outside. He's got a fire going, so he's trying to warm his hands. I'm sure maybe you've experienced this at some point where maybe your hands were cold and you put them near a fire to warm them up. So if you look up there at the top, you see the heat's going towards the person. So we always have to define in science like our reference point. So our system is what we call our reference point. So if this man is our system and the heat's going into the system, he's trying to warm his hand, that would be an endothermic exchange if the heat is being absorbed into the system. Now, if the opposite were true, if he were like touching a piece of ice, then the heat would go out of his hand into the ice. But you have to always define your reference point. So let's talk about heat flow. One thing about heat flow that you can always count on is it's always going to flow from high temperatures to low temperatures. Heat always flows from hot to cold. Always. So where you're sitting right now, if you were to put your hand on your desk and where you've not been touching it, it's going to feel kind of cool to you because your hand is warmer than the desk is. And so the heat's going to flow out of your hand, which is warmer, into the desk. And eventually it will reach thermal equilibrium, and that's when you really notice no temperature change at all. It's when the temperature of the desk and the temperature of your body have equalized. Once the temperature of two objects are equal and they've reached thermal equilibrium, heat will no longer flow in the system. Again, that's when equilibrium has been reached. A thermometer works on the principle of heat flow. A thermometer works on the principle of heat flow. Now, what I mean by that is most matter, most material expands when it's heated and it contracts when it's cooled. So if you think about a glass thermometer, and again, don't judge my drawing here, guys, I'm telling you, if this is a thermometer, and let's say this is the thermometer that has the glass thermometer has that liquid alcohol and it's got that little bit of alcohol maybe going up. So you have your thermometer. Whenever you put the thermometer, let's say at a flame, so this is a flame, it's going to heat the liquid in the thermometer up and the temperature is going to rise. So whenever heat flows into the thermometer, it's going to make the liquid in the thermometer expand and the liquid in there is going to rise. So you would see a rising temperature because the matter, the alcohol or the mercury or whatever's in the thermometer, the liquid that's in there, when it's heated, it's going to expand. And then if you were to put it in ice, it would get really cold. It's going to contract. So you would see falling temperatures in that case. So temperature is based on the uniform expansion and contraction that occurs with changing temperatures. Temperature is based on the uniform expansion or contraction that occurs with changing temperatures. That's why you see the thermometer rise and fall.